Thank you. So let me quickly share this, that today, for today's training, that in fact, it includes two sessions. Session one, the ES standard about heat treatment. The second one is another ES standard about the surface treatments. So just for quick understanding and for the basic knowledge sharing, I have prepared another two quick training slides about heat treatment and surface treatment. And so that I think it would be good for us and for you guys to have an easier understanding of our TTI's ES standards. So today's training is around 2 hours. I would divide our training into two sessions. First is about heat treatment, and second is about surface treatment. We would have a break after we finish the heat treatment session. So first of all, I would start with the basic training of heat treatment. Yep, here we go. So this is my training slide for both PRC and Finland, Milwaukee engineering training. Oh, hold on. I should do this way. It's about, okay. First, it's about heat treatment and failure analysis. And this is the traditional training inside the TTI I've held for our engineers. I would make it quick. Basically, we would start with 5 sessions. First, about the engineering standard, so-called ES introduction. Second, about the heat treating processing analysis. Third, failure analysis. Fourth, case studies. And the last one, appendix. First, about heat treating and failure analysis ES standard. Our ES or ES engineering standard is to guide the design engineers and of course also our suppliers to help them in terms of materials selections and heat treatment process for key components. Basically, it would be focused on 3 sessions. First, standardizing heat treatment requirements on professional tools. Second, better understanding of performance of heat-treated products for engineers and suppliers. Third one, guidance on failure analysis on heat-treated products. Basically, our ES standard system about the heat treating goes into these 6 different parts. First one about the carburizing and carbon nitriding. Second one about through harden and temper. Third about induction harden and temper. Then these above 3 ES standards are process related. Then the following 3 parts are steel group related. The fourth one is about the high carbon steels heat treatment. The fifth one is alloy tool steels heat treatment. And the last one is about spring and bearing steels heat treatment. Why would we divide those 3 different heat treatments for 3 different types of steels? Because of their specific requirements, both on the process setting and the microstructure, micro hardness control are critical and quite different with others. Here is a typical example of how TTI drawing defines those kind of requirement. Usually we would see that like in the notes, maybe the third one or the second one, we would see material is SAE 8620, and we see the heat treatment requirements. The process, carburizing, and here so-called K steps. That means the hardened layer, the surface hardened layer depth, then the surface hardness, core hardness, and of course, we have microstructure requirement. We see Below four items refer to ES, blah, blah. That means those kind of items are listed in the ES standards, and this drawing says all of those requirements must be met for this part. So we see the typical requirement like the surface retained austenite, carbides, intergranular oxidation, and core microstructure. And guys, please do pay attention, do pay close attention to this sentence that the below several items should refer to ES standard. These requirements are not clearly or detailed explained on the drawing, but inside the ES standard. But please be aware that those requirements listed in the ES standards are quite critical and are quite hard to meet. So if you are the first time or just the starting period of sample building with TTI, Binan, do pay close attention to the ES standards review and understanding. Please raise your questions, if any, about those critical items. Because if you don't spend that time and the dedication into studying our ES standards, sometimes there would be some misunderstanding of our requirement, and there would be argument. You would sometimes say, hey, our parts are good. Our other customers never have any complaint. But for TTI, our IQC would say, no, sorry, you are good, but your parts don't meet our requirements in the ES standards. So pay attention. Okay, then we move to a very basic introduction about heat treatment. So basically, it covers these 6 different sections. First, let's go to the heat treatment process and equipment. Here are some fundamental knowledge. Hello? Yeah, please. Oh, Vietnamese. Sorry, I cannot understand Vietnamese. Anything you can talk in English? Oh, if no, then I just move on. Here is some part of those definition of heat treating. Heat treating means heating some part. That means keep it soaking at a certain temperature and a certain cooling on a still part to obtain the certain microstructures, thus certain properties. Commonly, this about property we would put focus on hardness. Then types of heat treating. I don't want to go to the details of each heat treatment type, but just some words, maybe you can have some impression. Annealing and normalizing and so-called stress relieving, blah, blah. So basically on this page on the left, it's so-called the steel carbon phase diagram. And this phase diagram is so much complicated, so I wouldn't spend the time walking into the details. Right now, we only see that in simple, we would say with a different temperature setting, we can get different types of heat treatment processes like normalizing, full annealing, spheroidizing annealing, recrystallization annealing, stress relief annealing, and more. Basically, in our applications, I think those people, all of us who joined today's training, except some people from material group, we would not spend much time working on dividing each heat treatment process. We just need to know that temperature is the key for heat treating. Higher temperature or lower temperature would lead to totally different effects, and it would lead to different steel's properties. Yeah. So here is about other several commonly seen heat treating processes, like the third one, quenching, usually water quenching or oil quenching. That means heating some part to very high temperature, then quickly drops that or moves that parts into cold water, or cold oil, usually the temperature below 100 Celsius. Then we can get a very fast cooling of the part, and we can get the mechanical properties we want with the following up additional heat treating process. Tempering. Tempering is very commonly used. That is to keep the parts at a certain temperature, usually 150 Celsius to 400 Celsius, by holding them at a time for around 4 hours to 8 hours, we can get a balanced mechanical property of the steel with a good hardness and a good ductility. Ductility means the ability of the part to resist or to survive the mechanical deformation, falling, or quick impact loadings. So tempering is very important. And besides with the above four commonly used for steel parts, we also have solutioning and aging. These are commonly applied for stainless steel parts or our aluminum parts. So I don't want to go into very detailed. Here, let's take a look at the typical heat treatment process. It's about equipment. This page shows a typical so-called multifunctional batch furnace. This is, simply speaking, the very high price, high quality control, high production efficiency, and this type of equipment is TTI's normal or standard requirement for our heat treatment supplier to use for those parts with critical quality requirements. Or simply, we would say all of the parts used in TTI, if the service severity class is labeled as SA or MSA, which means very severe application or most severe application, we would require our heat treatment suppliers to use the multifunctional batch furnace for the heat treating. Without it, we wouldn't approve the heat treatment process. So please pay attention to this. This kind of furnace is always expensive, and the quality is always much more consistent than others. This is our preferred heat treatment equipment for our critical parts. Second one is so-called continuous mesh furnace, or sometimes we say it belt furnace. This furnace is simple like a channel. So the parts are loaded from the right side and unloaded to the left side. And the key is both sides, there are no gates. So the inner parts are would be directly exposed to the outside atmosphere, or we say air. So the temperature uniformity and so-called the inner atmosphere controller are far worse than functional batch furnace. So this kind of furnace for us is only allowed to be used in two conditions. First is for the through hardening or carburizing for the parts with low severity requirement, or we call it GA class. So any parts with GA grade requirement, you can go to the belt continuous furnace. And also another one is off tempering. Off tempering means the parts are quenched inside the molten salt bars. As far as we know, up till now, all of the off tempering furnace is using the continuous mesh furnace type. So for the tempering heat treating, we accept using continuous mesh furnace. This is the only thing. And again, we can see this is another example showing the continuous mesh furnace. This is the so-called the molten salt quenching, or we call it os tempering. And it seems we can see that from this picture, it seems the on-site flow management is not so good. So that's correct. Most of the time when people use the mesh continuous furnace, people would say, okay, the parts are of low quality requirement. So commonly, the flow management, the 5S management is not so good. Again, we would say if for TTI parts with higher severity grade like SA or MSA, we would require multifunctional batch furnace. Here, this page again shows the high-end heat treatment furnace, that is vacuum gas quenching furnace. This kind of the furnace commonly is triple or double the price of the common multifunctional batch furnace. Inside it, so-called vacuum, inside it during the heat treating, it keeps a very pretty low pressure close to vacuum so that no air is retained inside. That can give the much better surface quality of the parts. But of course, we know higher quality, higher cost. So this kind of furnace for us is not mandatory, but only for some critical parts we would require vacuum heat treating furnace. Again, besides with the multifunctional furnace and mesh continuous furnace and the vacuum furnace, we have another commonly used heat treating equipment, so-called induction hardening or induction tempering machine. This is only used for the local hardening or local softening of the parts we used. Basically, they are the motor shaft or sometimes spin output shafts. So small parts with sometimes one end or two end special requirements for the surface hardness. So here we are, we go back to this summary table. It tells us that each different equipment and what is the cost. We can see in this table, continuous furnace, the mesh furnace is of the lowest price, that is baseline 1. And the multifunctional batch furnace, 1.5, that means 50% higher than the mesh furnace. Then for the os tempering, also pretty high cost, close to multifunctional batch furnace. Vacuum, surely higher cost. It's about 2 times of the continuous mesh furnace. For the induction, the cost is also high. Pay attention to this. Why? Because most people would say induction hardening is quick, it's low cost. Why? The overall cost is still high because of the efficiency. For the induction hardening or induction tempering machine, the process is done piece by piece, pretty low efficiency. Even though the equipment is low price, even though the process handling is quick, but the overall, every piece, the heat treating time period is much longer than the continuous mesh furnace because that process is done by batch. That means you can heat treat more than thousands of pieces of parts together. So again, lowest cost for continuous mesh furnace, highest cost for vacuum multifunctional furnace, and of course, still the quite high cost for multifunctional batch furnace and induction hardening machine. Here we go, move forward. It seems that what about the steels we commonly use? So it's a very big topic. I don't want to go into very details, but just pay attention to the carbon content. For us, for TTI applications, low carbon means the carbon content is lower than 0.25%. We normally use carburizing heat treating. That requires multifunctional batch furnace. For medium carbon, that means the carbon content around 0.45%. It uses through hardening and tempering. So that is dependent on the severity class we require. For low end, that means GA, mesh furnace is okay. But for the high end, that means SA or MSA, multifunctional batch furnace is a must. Here again, this table just gives us a very rough process setting for heat treating. Overall, we can say for the steers, we have to heat the parts to above 800 Celsius and hold it to maybe 4 hours. Then we can quench them in oil. Commonly, we use oil, quenching oil, and we can get different kinds of the mechanical properties. And here again, this page shows the typical carburizing heat treatment process for the low carbon alloy steel. This is the typical one, SAE 8620 or GBT 20 CrNIMO. That means 20 chrome, nickel, molybdenum alloy. This is the most commonly used steel in TTI. And we see that for the heat treating process, it covers 3 steps, so-called carburizing and quenching and tempering. So we can see the temperature has 3 steps. For carburizing, around 900 Celsius. For quenching, around 850. And for tempering, between 180 to 200. Overall, it can give us a very balanced mechanical property of our part. And here, take a look at it to the right side for the typical requirement. We can see the C steps, that means K steps, with the criteria of above 513 HV. TTI is quite tough at this kind of requirement. Our spec is 0.2 to 0.4 millimeter, quite narrow range. Pay attention to it. Sometimes it would go out of spec. Surface hardness, 650 to 750 HV. It's a commonly applied requirement. And so-called the boosted carbon potential, CP. That means the carbon potential at the high temperature. Commonly, it's 1.0%. And of course, there's another step, so-called diffuse CP. That means the carbon potential during the quenching period, 850 Celsius. Commonly, it's about 0.7 to 0.8%. So that's overall this process setting. And again, I would say here that it seems a little bit boring, but in fact, most of the time, us, especially our suppliers and also our NPD stage and also MP stage, we have troubles on the parts with some out of spec testing data. That would bring huge trouble. And here's another one. It's about through hardening. It's about the middle carbon steels. So the temperature and the settings, I don't want to go to their details. And surely, different types of the steels, different heat treating process requirements. But overall speaking, the temperature is around above 850 Celsius. And again, this is a very typical example of our parts. This is SAE 4140 or GBT 42 chrome molybdenum. This is so-called middle carbon alloy steel. And the temperature of the heat treating process is through hardening. So we see it covers only 2 stages. First, quenching, the holding temperature 850 C. Then the second, tempering, is about 300 C. And here, for the quenching or the heating, the carbon potential here on the right it is labeled as austenizing CP. The carbon potential 0.4 to 0.5. It's this carbon potential gives a protection atmosphere of the surface layer during the high temperature so that no defect happens. Okay, I would say once again, this page it would help me quite a lot in the coming days when we have troubles of the heat treating. We all know heat treating sometimes would make troubles. When we have troubles, we need to go back and review with all of the process setting like this. And here, the spring steers. And here he has very famous one. It's so-called the ductility and the toughness. I don't want to go to details, but simply speaking, this is very commonly seen. On this page, we can see those kind of the steers and spring steers and alloy spring steers. It has quite a different requirement with our other steers. We can see that the quenching temperature would go down to low temperature of around 820 only. And here, this is maybe not the most important, but is the most commonly seen example of TTI's application for steers heat treating. That is GBT 65mm, or in SAE it is 1566 spring steel plate. We use them so commonly in our stamping parts. This is an example of that. For here, we use tempering heat treating process. That means the parts are heated up to 850 Celsius and it drops into molten salt baths. Or that means the liquid made of salt, the temperature around 250 to 260. Please pay attention to the time inside the salt bath. It requires 15 to 45 minutes. For other parts, for quenching, the time duration inside the oil tank doesn't play that big role, but for oil tempering, this time duration inside the molten salt bath is key for our success. What is the impact? If the time period is too short, we don't get the good ductility or the good mechanical properties of the parts we wanted to have. If the time period duration is too long, the trouble is about the cost, because the longer you stay inside the bath, the longer or the lower efficiency of the production line. But overall speaking, for us tempering process, time is a must. We need to make sure the parts are soaked inside the molten salt bath for at least 15 minutes. And usually the upper limit is 45 minutes. And the last one is about the bearing steers. Bearing steers is of the toughest quality requirement for the service. And this is the list of what we see. And again, we see very famous example, GCR15 or SAE 52100. This is for the bearing bores and with a critical requirement of that fatigue strength. So here we are, the third example of the typical steers for heat treating, that is GCR15 and SAE 52100. We have the heat treating. We see again for us tempering. So we can see that on the above, we have the holding temperature around 830 Celsius and put it into molten bath. The molten bath temperature is around 200 to 260 to 270. And the time duration, again, we see this value, 15 to 45 minutes. All right. Up till now, I have gone quickly into the heat treatment process, quick introduction. So team there, do you have any questions? Do you have something you are interested to talk here? All right. If nothing more, let me go to the second stage. It's about the heat treatment ES standard review. So I guess you guys all have this year standard on your hands already. So let me quickly go inside it because go through it because this year standard covers so much. So this year's 00636, it covers all of the iron-based powder metal raw materials and heat treatment processes. So I guess that our current today's focus is mainly about the powder metal heat treating, right? Okay, I would just move on. Maybe we have to do it in this way. So I guess you can see it. So first is about this content. This is a list of the commonly used raw material for the powder metal. In the previous 30 minutes, I just introduced about the heat treatment processes. It doesn't have any specific differences of the raw material processing methods. That means machining, casting, or forging, or high pressure die casting, or powder metal. Every process for the heat treating, basically they are the same. So this firstly gives a rough introduction of the raw materials we TTI allow to use for our parts. So it's not such a big list. And here we are, we can see that different alloy types or even the same alloy type, we have two different subgroups like ADHT, 90HT, or here 105, 135, 11555. What is that? It gives the different strength, ultimate strength of different subgroups with a different density and of course with the different mechanical properties. How they can make it, firstly about the powder metal process, secondly about heat treating. So we move on. This section covers some illustration or we can say engineering training for different groups of the material so that anyone who's doing business with TTI can understand what we require at what we are focused. So it's always for powder metal, it's always about the sintering process, the heat treating, and also the powder metal, the porosity control, the density control. All right, we don't go into those details because it takes so long time, but basically it covers everything. Okay, then we need to take a look at the heat treatment and microstructure specification. Here, let me go into this summary table. This is more helpful, I think, for you guys compared with those so much words there. Basically speaking, for TTI's powder metal parts, we divide them into three different grades based on their service severity. GA, that means normal. SA means tough. MSA means the toughest. Different grade, we have different requirement. And you know, higher grade, more requirement and the tightened spec. So let's look at the MSA. That means the most severe application. We have limitation, we have requirement upon four different sessions. First about density, second about hardness, third about porosity, and fourth about microstructure. Each one matters. So for the density, we know that for the MSA, we are not only require the average density, but we also define our spec on local density. That means basically we would say every part, every different locations, we are expecting to get similar, similar consistent hard density. For the hardness, always we would talk about the outer surface hardness and the local core microharness. And here, because of the special features or the intrinsicity of the powder metal part, that means always lots of small particles inside, lots of porosities. So we rely heavily on microharness. That means Vickers harness testing. And for the core, for the overall so-called macro harness, HVRC, commonly it is only accepted for reference, not for OK or NG charge. Why? Because that testing requirements is not consistent. And the third one, sure about the porosity. It's a defect. So for MSA, the most severe application, we don't accept micro crack. And we would check the porosity at the specific defined area to make sure no trouble there. And the last one is about the microstructure. We don't accept sintering defect. We don't accept surface decarbon, so-called surface decarborization. And also, we don't accept so-called the surface non-martensite microstructure. This is pretty tough requirement. It defines that within the surface layer less than 3.0 millimeter, we wouldn't accept any abnormal microstructure except for martensite with a ratio higher than 5%. It's pretty tough, so we will explain later. This table gives the overall requirement of TTI's heat treating process for powder metal parts. Then, of course, after that, for powder metals, you would have to do the oil impregnation and anti-rust treating. So here it gives some kind of suggestion for that. I think today's training is basically focused on heat treating, so we would leave them alone. And finally, surely we have surface treatment for powder metal parts. That would be the next session of today's training. All right, we go to the density. Detailed requirement for density, it is listed in Milwaukee's IQCWI. It is basically in accordance with ISO's testing standard. And please pay attention that this gives only the overall density of the full part, not a local one. Secondly, it's about harness testing. Harness testing, we know it's micro harness testing. Sometimes we call it Vickers micro harness testing. For powder metal parts, because of the existence of multiple or many small porosities or pores inside, so the harness testing is easy to get fake reading, or that means some results are not reflecting the actual harness. So usually we would do in this way that we need to measure for each part, we measure 5 different points for the harness reading. And we would remove the highest and the lowest reading. Then we get the average of the remaining 3 points to serve as the testing results. And actually for us, usually in our lab, we would measure 7 different points of the harness. And we would remove the highest and the lowest 2 ones. Then we can put the average data with the remaining 5. And of course, for the loading force of Vickers, because it matters so much. So commonly, we would recommend for 100-gram force or 200-gram force. That can give us much reliable harness testing. Pay some attention here because this kind of the 5 or 7 points harness measurement and removing the highest and the lowest, but keeping the average of the remaining 3 to 5 as a reading. This kind of complex handling is only used for powder metal parts. And here for the next session is about the microstructure. Microstructure sample building of course, we needed to do the cross-sectioning. So hope you guys have already established those kind of the capability inside of your lab to wire cutting the parts, mounting it, grinding and polishing it, then chemical etching it until you can get a very clear and the sharp image of the microstructure to tell you what kind of defects are there or to tell you how good your microstructure is. So about the defects inside the powder metal parts after heat treating or before heat treating, let's go step by step. First one is about the defects associated with sintering. That means the defects which could be found after sintering. Yep, here we are. We can see those two typical images of the defects inside the powder metal parts after heat treating. We can see that first bottom left image, it shows that in the center a large circle shape of white and with some kind of the black dots alongside like a circle outside. This is a typical so-called poor sintering or incomplete sintering of the powder metal particle. So the particle's outer perimeter or the outer boundary can be seen clearly. This is NG. And second is about the crack along the grain boundaries. That means this kind of things, if the parts are heated up to the 1100 Celsius or 1200 or higher temperature, if the parts contact the cold air too early, then this kind of the fast cooling would lead to the local cracking or the separation. So this would be a major defect. Then the second one about microstructure, for sure it's about porosities and the percentage of porosities. This kind of testing can be only done with microstructure cross-section analysis. Please here pay some attention to the sample or to the specimen preparation skills. For powder metal, to grind and polish open of those porosities to let us clearly see how this porosity looks like and how it is distributed inside the base metal matrix. It has some tricks or it requires quite a lot of experiences of the technician or the engineer. Pay attention that this kind of the images cannot be achieved easily. It requires special training on site and it requires some sort of the experience accumulating. That means your technician or engineer, after they got some the quick training and got certificated of the third party, they still have to spend some time or several months working in the lab, working on the powder metal FA cases before they can finally get certificated to carry out the microstructure analysis of the powder metal parts independently. It's quite tricky. And here we can see the condition changes. On the bottom two sides, we can see the black, like the river or the lakes. They are lying just on the outer surface edge. It gives so-called the open porosity. This kind of defects, this kind of the feature is defined as defect, not acceptable. So that means we are expecting to find the powder metal part surface continuous and solid, not divided by the large porosities just on the edge. Then another one is called decarburization. Sometimes we just simplified saying decarb. Decarb means that the surface layer of the steel gets pretty soft because of the high temperature staying in the air. It would reduce the hardness of the part and also it would largely destroy the life performance of the part. So it's a severe defect. Let's take a look at it. For that, we needed to do some kind of the microharness testing to make sure the surface layer hardness is still good, and it can give us the reliable performance of our parts during the live usage. Next one is about surface retained arsenide, or so-called nickel-rich arsenide. This kind of thing, I would say this way, pretty tricky. We have those images. We can only see that on this microstructure images, those white and shiny area, we call it retained arsenide area. There's no so-called monazite microstructure. So those retained arsenide is pretty soft and it would easily get cracked in surface. So we strictly control this kind of the content in our parts. It can only be done or be caught under the microstructure with high magnification. 500 is the minimum, sometimes even 1,000 times. So it is heavily related to the specimen's surface quality after the grinding and etching. Always say it requires a lot of experience of the technician or the engineer working in the lab. So it's not that easy. And the fifth one is about so-called the martensite near the surface. It's not that bad, but usually we need to control it. And of course, the last one, carbide networks. This one commonly you wouldn't expect to see, but sometimes if the heat treatment process control is poor, we can see it. So those two images gives the carbide networks. We can see on the left, you can see like the spider net, the shiny white, those thick layers. It is so-called the carbide network. This network is fragile, very easy to crack. Even though the harness is good, but the brittleness is so strong that we don't want to see it. It's not accepted. On the right side, we see those large, white, like the particles, like small rocks broken into pieces. Those are also brittle and pretty hard parts there inside. It would destroy our parts ductility, so not desired. So last one is about perlite. If the heat treatment process is so bad that we would see those kind of perlite structure there, but basically it's not a big concern for our suppliers at Vietnam now because of the heat treating equipment. The furnace is quite reliable. And here, last one, maybe the ferrite. Ferrite is sometimes something wrong with the process, but basically we will see if under the microscope we can see some individual large particles, pretty white and shiny, and if we measure the hardness, it's pretty low. Though they are called ferrite. So ferrite is pretty of low hardness and strength, not good for our parts performance. The number 9 is about the copper used in the old version or the old design of powder metals to increase the density of the part. But now we are limiting this kind of the application for the copper, so maybe not that a big concern. We see on this image on the right side, you see those red colors, those tiny spots. Those are the copper, pure copper. So if they are exposed to the surface, not good for our parts. Okay, so I think now I just quickly go through the powder metal heat treatment process and of course, a quick introduction of our ES standard upon the heat treatment for powder metal parts. So, hey guys, do you have any question or do you have any topic to talk? All right, maybe I think, please, hey, please, go
Yes,
ahead.
Dominic, I just want to ask PMV if they have any questions in Vietnamese.
Okay, please.
Team PMV ơi, bên mình có câu hỏi gì không nhỉ? Okay, nếu không thì bác training tiếp nha. 2 minutes, so PMV
Okay, please.
doesn't, yeah, PMV doesn't have question for now. Oh, I just have a question like, will you share the training slide today after the training?
Sure, I would.
Okay, thank you. So, please keep going.
Okay, so thanks for the first session of today's training. I would suggest that we're having a short break. So from now and we could resume after 10 minutes.
Okay,
10 minutes
thank you.
later. Okay.
Yep.
Yeah, we'll come back later.
Yeah. Mọi người ơi, bây giờ mình sẽ nghỉ khoảng 10 phút và sau đó thì tiếp tục phần training thứ hai nha.
Hi, Ellie. Hi, hello. Can we start now?
Hi, Dominic. Yes, we can continue the training.
Yep. Okay, thank you. Thanks everyone for staying with us, and let's go to the next step. That about surface treatment. So basically, first one about the quick introduction of surface treatment. And above all, I would say this one. That is a key summary table for all of those requirements of various types of heat treatment processes which are listed in our year standard. That means a comparison of anti-corrosion performance of different heat treatment processes. All right, that's it. What is that? That gives the anti-corrosion performance of different types of surface treatment, which are used in TTI based on our ES standard. What is that? Basically, we would say in this way, all of the surface treatment on steel parts, basically they are designed for good anti-corrosion performance most of the time. Of course, sometimes those surface treatment can give us additional performance of anti-wearing, but for TTI, most of the time, the surface treatment is designed for anti-corrosion. So here are the 10 types of the surface treatment process we normally would use. Here we see black oxidizing, phosphating, then zinc plating. For zinc plating, because it covers such a large family, so it have different colors. Black, colored plating, white, and also for the next one, the fourth one is nickel plating. Nickel plating also has a black nickel and the white nickel. Then we go to electroless nickel plating. It's much more expensive, but also performance is excellent. Surely we then have other several different processes like electrophoresis plating, dichromat plating. Dichromat, we would pay some close attention to it because it is quite preferred in TTI. And of course, we have paint spraying, powdering, and steam treatment. All right, so for us, how can we make a choice of different surface treatment processes? What are the main pros and concerns we would think about? Now we see this. On the right side of this table, we can see the most important performance of our parts with surface treatment. That is the time duration at neutral salt spray testing, so-called NSS testing. Simply, we would say longer the time, better the performance. So we can see on the right column that we have two best candidates that are number 5, electroless nickel plating, and number 7, dichromat plating. Basically, we can get more than 120 hours of neutral salt spray testing performance. And after them, we have others that is electrophoresis plating, 96 hours, and then we have zinc plating, especially the black zinc plating. We have the performance longer than 72 hours. And with all of about those extraordinary good plating surfaces processes, we have the next one like zinc plating of color and nickel plating. And by far, the lowest requirement or the lowest performance of anti-corrosion under the neutral salt spray testing is black oxidizing. Please pay attention to that because most of the time, powder metal parts would go through black oxidizing or steam treatment. Those two processes only provide a very limited protection of anti-corrosion, only around 6 hours under the salt spray testing is pretty poor. So this kind of surface treating our treatments are only designed for the anti-corrosion performance during the transportation of the raw parts to the assembly line. It cannot provide any guaranteed performance of anti-corrosion in service. So I guess you guys would have some kind of end user complaint of corrosion or rust with parts after black oxidizing. That's commonly seen. And above that, we have the second option like phosphating. It can give us a balance of cost and anti-corrosion performance. So this can achieve around 24 hours salt spray testing, which is quite acceptable most of the times. But if you still have some higher requirement for the neutral salt spray testing, we have to go to electrolytic plating of nickel or zinc, or we go to electroless nickel plating. And of course, dichromatic plating is always an option. Here we are about the surface treatment. For powder metal parts, maybe it's not a big concern, but for other steel parts, here's a big concern, so-called hydrogen embrittlement failure. What does it mean? That means the parts, especially with the thread structures, it can break, can crack without any usage, only after assembly in line. After 1 to 7 days, it can crack, can break without any kind of the mechanical loading. That would be a huge trouble for us. So in our year standard, in surface treatment, we have very clear requirement. Let's see it. So any steel parts, basically it should be martensite or ferrocite. Always say stainless steel, if from austenite, there's no concern about that. But for any of the steels of the ferrite or martensite structure, with a core hardness higher than 32 HRC or the surface hardness higher than 35 HRC, we request the hydrogen annealing heat treating process. Usually it should be 200 Celsius and 4 hours. And it must be done within 1 hour after the parts leave the electrolytic plating line. The shorter, the better. So this kind of the requirement is commonly applied for all of the parts for TTI. So that means any steel parts with the surface hardness higher than 35 HRC or the core hardness higher than 32 HRC, it must go through the hydrogen annealing heat treatment immediately after the plating. The hydrogen annealing heat treatment process is commonly set at 200 Celsius, 4 hours. So this is a must. Without it, we would have huge trouble, both for our production line and of course for our suppliers. So pay close attention to it. And here, there's another red line for our parts. Any parts, steel parts, if the hardness goes up to 50 HRC or above, we strongly limit or prohibit the application of electrolytic plating or some kind of acid pickling, if any. But for sure, there's some kind of the single cases which can use this. Basically, that requires so-called no continuous tension stress. But this is quite complicated and it requires a lot of experience and expertise. So for our cooperation teams, for our suppliers, if you see any drawing with surface treatment like zinc plating or nickel plating, but the part surface hardness goes above 50 HRC, you need to understand it's a big trouble for you. There would be huge risk of hydrogen embrittlement crack. So please raise your hands and feedback to our teams saying, hey, this kind of drawing, it seems there's some kind of violation to TTI's ES standard. Is that okay? Would you please double confirm? Please do that. That would both help you and help us. We don't want to get into the huge trouble of hydrogen embrittlement. So here, summary again. If for anything, any surface treatment parts with electrolytic plating of nickel and zinc or acid pickling, if the steel's surface hardness goes up to 50 HRC or higher, it is not allowed unless you get approval from TTI group. This TTI group means engineering group, not only the QA group. Please be aware of that. And here we go to some samples of different surface coating. Here we can see some samples of dichromatic coating. Dichromatic coating is the mostly preferred coating process for us if for the high hardness steel with excellent anti-corrosion performance. We can see under the cross-section of the microstructure, we can see that a very uniform, a very thin and a good adhesion layer, plating layer on the outside. The thickness around 17 micron. And also we need to understand that to get this clear image of the coating layer thickness and the surface structure, interface structure, we need to get an optical microscope with good performance that can give us the clear and sharp image of the microstructure under the magnification of 500 or even 1000. Without that good optical microscope, you can never make a judgment of whether the coating layer is good or not. And that would go to a big trouble if the actual data is not reliable. Here again, we can see that if for dichromat coating, because it's dip coating, that means the parts are loaded into the liquid and then dries out. Any of the concave shaped places that would have a much thicker coating layer. Here we can see at the root of the teeth, we can get a coating layer thickness around 62 micron, almost triple the size of the flat surface outer. That means dichromatic coating, it has some limitation that the surface coating layer thickness is not that uniform. All right, then we go to a process introduction of typical surface treatment. Firstly, it's about black oxidizing. It's a demo sample. We can see that it can be done manually with a basket and holding the parts, just like cleaning our clothes. You dip into one bath, rinse it, and move to next, and finally into a chemical reaction bath with some additives into the water solution, and hold it for some time at a certain temperature. Then it's done. So it's quite quick, and it's not that complex to manage. So it's a fast, low cost, and minimum anti-rust protection, black oxidizing. Secondly, it's about phosphating. This we can see on the right side, also similar ones, but the parts are hung in a rack, or we can see a supporting fixture. So every part they can get individual space and without contacting each other during the reaction inside the water solution. And pay some attention that the phosphating surface is not that robust or solid as we think. In fact, we see under those images that is SEM image with magnification around 4,000 times. We can see a layer, a phosphating layer like some small crystals or small rocks or sands on the surface. That means the surface coating layer, phosphating layer, is both coarse and not that solid. So the anti-wearing performance is not that good. And also because of those porosities existing on the surface for the phosphating parts, usually we would add dipping inside the anti-rust oil to get a sealing off effect of the surface gap so that we can get a very stable anti-corrosion performance under the salt spray testing. And here, this is a vivid example of the modern automated electrolytic plating, that is zinc plating line. On the right side, it's a very good factory, a plant of electrolytic plating. And we see that on the rack, we see the parts with the shiny gold color. This kind of the various types of color can only be found on zinc plating lines or the zinc plated surface. With some special fine tuning of the chemical additives inside the water tank, we can get different types of color, from gold to silver to blue to bluish to yellowish to black of the zinc plating layer. This is the biggest advantage of zinc plating. That means you can get various types of color you need. And it's all combined into this plating layer. You do need to add a special additive or additional coating layer so that the cost and the quality can be assured of the parts. Here, this is an illustration of the zinc plating or the nickel plating process. Basically speaking, this kind of electrolytic process, coating process, it was developed by Mr. Watt in almost more than 100 years ago in US side. After that, basically that recipe and the process doesn't change a lot, but only some special chemical additives are developed and applied for this plating process to get a better surface cosmetic and appearance, and of course, the reliability of the coating layer. But the basic principles keeps the same after more than 100 years. And here we can see that for the electrolytic plating, this gives us why something happens, so-called hydrogen embrittlement. That means by some research, we do understand that during the electrolytic plating for nickel and for zinc, some kind of active hydrogen atom would generate because of the chemical reaction, and that those items can dissolve into the steel matrix, and those kind of atoms, hydrogen atoms, later on can regroup and form those kind of the hydrogen like small bubble on the grain boundary, and that generates the high pressure and lead to the sudden crack of the parts. This is so-called hydrogen embrittlement. And again, this we can see after the plating, we can see the surface layer. So anyway, it tells us with the changing or the fine-tuning of the electrolytic plating processes, like the electricity and like the void, we can get a good and uniform and consistent coating layer. And that gives us a very reliable performance under the neutral salt spray testing. Again, this is an example showing how this is electroless nickel plating, or sometimes we call it chemical nickel plating. It goes some similar way of the working like the black oxidizing or phosphating. That means tank by tank, an operator just needed to put the parts on a rack from one tank to another tank and just keep them inside of the tank for several minutes. And when the parts go through the last tank and get dried out, we can get the plated parts. So it seems quite easy, but you know, actually when you visit some electroless nickel plating workshop, you wouldn't feel so good because of the chemical, the acid moisture inside the air, and some kind of bad smell and hazardous and those vapors inside the workshop. So anyway, this plating process is cheap, is expensive, the quality is good, but the coating efficiency is pretty low. So the cost is much higher than the electrolytic plating. And here we go to some other traditional coating. For this one, it's so-called the electrophoresis plating. This is commonly used for the automobile, that our car, the doors, and all of those plates, the final painting is done by this kind of electrophoresis plating process. It's reliable, it's good, but the investment of that line is huge, so the cost is also a big concern. And here we can see the silver-white color dichromatic coating. Dichromatic coating is specially applied for our fasteners, that means screws or bolts or nuts. They can give us a very much excellent performance of anti-rust, anti-rusting. And there are only two concerns. First, cost. Dichromatic plating is the cost is quite high, much higher than the traditional electrolytic plating. And of course, we can also know that the surface coating layer thickness cannot be achieved that uniform as electrolytic plating. So if for some parts we have very tough requirement of the dimension, that would be a concern. And surely, finally, one would be the, of course, the investment of that line. If our supplier is willing to do that, it's good, but for others, not so good. And final one disadvantage for dichromatic coating, the color. Now we can get only the typical silver-white color, no other colors. If we wanted to get other colors, we have to apply additional coating or plating. That would be a big concern of the cost. All right, this one, typical one, we call it painting. So just some paints, and with the spreader, we can paint everything with whatever we want. So this is a common process. So anti-corrosion performance is good, but because of this painting process, the painting layer thickness is always high, around 100 micron or higher or thicker. That would be some concern for our parts, because our parts normally we don't want those kind of deviation. And last one, so-called the powder coating. So again, quite commonly used for automobile, for those kind of the architecture, or for those kind of the civil buildings. But this kind of coating, powder coating, has very tough requirement, especially at Vietnam and in China and in Europe, about the EHS, environment health protection. It's easy to explode. It is pretty much hazardous for the operator's health. So this line requires a specific approval process of local governments for environment protection, and always the investment is huge. So commonly, it depends. If we can have some good supplier with this kind of plating or coating process, it's good. If nope, that we need to think about other alternative methods. Okay, last one. It's about our ES standards of those powder metal parts, about the surface treatment. For powder metal parts, commonly we use the steam treatment. How to do that? Simple. Just put all the parts in like an oven and pump in the high temperature, the steam. That means the water steams, and the high temperature steel would react to the moisture, the vapor, and it would form a beautiful black color that is iron oxidation layer, and it can give us a minimum anti-rust performance. But again, pay attention, this is just a minimum. It can give us some safety of the parts anti-rust during the handling and during the transportation, but it cannot give you any warranty of the parts anti-rust during the service. All right, one big trouble for us and sometimes we don't have some kinds of the close attention to it. That is acid pickling. Sometimes we call it acid pickling or acid cleaning. We know that for us, for TTI parts application for surface treatment, hydrogen embrittlement fracture would always be a big concern. So we have very strong limitation about electrolytic plating. But sometimes we know that our supplier would need to apply strong acid cleaning or so-called acid pickling before the parts are put into the coating line so that the surface oxidation, surface gear, or any kind of contamination can be removed. That can give us the parts good quality, but this strong acid cleaning or acid pickling process would bring itself a huge risk of hydrogen embrittlement. So we have very strong limitation about acid pickling. Usually, we would require the pickling time within 2 to 5 minutes. The shorter time, the better. The longer time, the higher risk of hydrogen embrittlement. And also we see that the chemical composition is usually a mixture of chromium, hydrochromium acid with water. And the pH value usually 0.1, pretty strong acid. Please do control the acid value and of the rinsing water after the acid pickling. And also, please monitor the time duration inside of the pickling. All right, and for the surface treatment, we need to see some kind of the solid spray testing, because I know that you would have some trouble about the argument of surface treatment, those solid spray testing performance of the parts under surface treatment. This is a vivid example of us taking some kind of solid spray testing at our supplier to study the anti-rust performance of parts of screws with dichromatic coating. Here it shows how we put the parts inside. And this example tells us what is bad. Those kind of red color on the screw surface are rusts or iron oxide, steel oxidized. They are failures. It is an example of failure under solid spray testing, only 24 hours. All right, so let's talk about hydrogen embrittlement fracture, how to handle this. Please, I do know that our suppliers are trying to do every effort just to want to make things right, but sometimes even though none of us wanted to see that, we would see those kind of the hydrogen embrittlement failure. This is an example showing how it goes wrong in TTI parts with those kind of hydrogen embrittlement. We see the cracks, we call it intergranular cracks, and we see those kind of the small white marks on the surface and also some small holes. All of this contribute to the solid conclusion that this is hydrogen embrittlement. So let's be clear that again, any parts which goes to hydrogen embrittlement failure, we TTI, our labs, can send the parts to the SEM analysis. We can get very solid evidence of whether it is hydrogen embrittlement or not. So don't make this kind of trouble. It would cause you to receive a very high amount debit note. That's something both of us don't want to see. Okay, so I think this is just some example showing how the line is managing. In fact, this is the supply side, that is a supplier with fasteners on northern side at Haipeng City. So we audited it and we checked everything there. And that's an old time. We can see that those tanks are those water, without anyone noticing that those water have been severely contaminated and goes to the severe acid. That gives a lot of trouble. it brings a huge risk of hydrogen embrittlement because acid pickling. Then after that, we help them to do those kind of correction, and after that, we can see that all of the rinsing water is all okay right now. But at that time, it gives a very vivid example of how things could go wrong if we don't monitor the control the so-called the acid or the content or with the pH value in every tank inside of the plating line. All right, last one. I just wanted to make it short, but sometimes we would face the trouble of the coating layer peeling off or the adhesion no good. So here we follow the ISO standard, and it gives a very large process testing table with different plating processes with different adhesion force testing method. Sometimes we use the chisels and scribe testing, and sometimes we use the thermal shock. Whichever is easy to apply is all good. First, about scribe and grid test. It's easy, just like to cut the coating layer with a sharp knife, and let's check how they look like. It's a typical way. But here we have another way. That is thermal shock test. That is to put the parts into oven, hold it up to 300 or 250 based on different types, and then drop them into the cold water and to check if the surface layer still good, stays good. That means no peeling off, then the result is pass. Yep. And finally, we both know that for TTR parts, we have a very commonly used testing method, so-called cross-hatch test, a scribe test. So we can have special knife and cut the vertical and horizontal lines and check just like this. We just make sure that all of the cuttings are clear, no small grades are peeled off, that's good. But if that goes wrong, we would reject all of the batch, the whole batch. Okay, I think this is all for the training and surface treatment. And so, hello, please. Do you have any question about that?
Team PMV ơi, bên mình có câu hỏi gì về liên quan đến surface treatment nhỉ? Xử lý bề mặt thì em có thể hỏi bác Dominic. Ừ, ừ em nói đi, mình sẽ về ra. Ừ. Em cũng thể một ví dụ phương pháp mạ là mạ gì với cả bạt nào nữa thì chị gửi cho bác hoặc là chị show cái bản vẽ lên cho bác sẽ nói ấy. Ừ em, nhưng mà ví dụ là em đang nói về phương pháp mạ gì, mạ điện hay là mạ kẽm hay là mạ gì á? Kẽm là hi Dominic, so PMV they have patient with the perimetal pass.
Yeah, please.
They have some difficulties when doing chest plating.
Which one?
GN chest plating.
Chest
G,
plating? Jet
yeah,
plating?
yes, GN plating. I just take.
GS plating, which one? Hold on, let me check. Powder coating, steam coating, paint spraying, which one?
Um, it's like coating uh GN GN plating. Wait, I need to check the word.
Yeah,
Galvanized galvanized plating.
carbonizing.
Yeah,
Uh,
yes.
what's the meaning of carbonizing? Anything listed in this page? This covers everything.
Um, can you scroll down to the table? So
Okay, let's see. I know, I just want to make sure. Yeah, which one?
this is the number three. The number three.
Number three,
Number
that is
three. Yeah.
zinc plating,
Yes. Zinc
ZN
plating.
plating.
Yes. So
What's their trouble?
so vendor said that when they do this fishing, they cannot meet. They have some difficulty and cannot meet the drawing requirements because the battle metal have many parts. Parts. So
Porosities,
part.
porous? What's their difficulty? I
I
think
mean, like the empty bubble inside the part, the
inside of the
porosity, the
porosity.
empty. Yes.
What's the meaning of MT? Do they have
Uh,
any images or any slides that can show me?
yes, I'm asking them to provide the part numbers or the pictures to show you.
Yeah, because usually for our parts, we only stay focused on the NSS test, the salt spray testing, and
Mm.
sometimes just the layer thickness. So others usually no troubles at all.
So how about zinc plating, like for powder metal? Any recommends if they,
Ah,
if, yeah.
I understand. That
Mm.
means our drawing requires zinc plating for powder
Yes,
metal parts, right?
yes.
Okay, for powder metal parts, there's a special process called impregnant, impregnment, impregnment, something like that. What's the meaning?
Mm.
The powder metal has a lot of porosities on the surface. They
Mm.
cannot be directly put into water.
Mm.
It's not
Okay.
working. They have to be sent into like epoxy or some kind of chemical liquid bath to have all of the surface porosities covered or sealed by those chemical agents,
Mm.
then dry them. Then they can put it into electrical plating. We call
Okay.
it impregnment or sometimes sealing process to make all of the surface porosities covered by some chemical agent.
Okay.
Yeah, this is special
So
one. Yeah,
for zinc plating, right?
for all of the plating, zinc plating,
Uh,
nickel plating, if they want to do plating, they have to do that.
okay. So for the sealing or impregnation, so what kind of chemical liquids here that's vendor should use to cover all the surface porosity?
Usually it is epoxy,
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 epoxy. Can you
epoxy,
type epoxy?
EPOXY, epoxy.
E- Epoxy.
Yeah. Epoxy is a special chemical widely used in the world, polymer type. It's liquid at the room
Mm.
temperature, and when it is heated up to 120 or 150 Celsius, it can transform into solid like glass. So this is commonly used.
For the temperature, can you repeat again about the temperature? Right.
120 Celsius or 150 Celsius.
Okay. Okay.
Yeah,
So let me translate to the vendor.
yeah, please.
Thái ơi, thì bác Dominic á, bác có trả lời câu hỏi của em về việc mạ kẽm hoặc là mạ niken nhá. Bác đang nói về mạ chung á. Thì đối với những bà Pyrometal trước khi đem đi mạ, bên em cần phải có qua một quy trình xử lý đặc biệt là em phải nhúng bạt ờ, vào trong một dung dịch hóa chất tên là thường là epoxy để cho cái hóa chất này nó sẽ làm đầy hết những cái mặt sống từ cái lỗ xốp ở trong con bạt pyrometal. Sau đó em mới mang hàng để đi mạ kẽm hoặc là mạ niken được không? Nhiệt nhiệt độ thì nhiệt độ về cái nhiệt độ epoxy dung dịch là ờ, từ một nung từ 120 đến 150 độ thì nó sẽ hóa lỏng, nó sẽ có dạng hóa lỏng giống như lớp glass. Glass thì chị cũng không biết gì cả. Nói chung là nhiệt độ cho cái lớp epoxy này á thì nó hóa lỏng á, từ nhựa xong rồi hóa lỏng ra là 120 đến 150 độ C. Thì chị không biết ở ngoài Bắc em có vendor nào mà có thể làm được cái nhúng epoxy này không? Bên em đã thử tìm hiểu xem. Ngoài ra em còn câu hỏi gì nữa? Hi Dominic. So thank you for your
Yeah,
answer. Yeah.
yeah.
So PMV just have that question.
Okay. So I think, thank you, Ellie. And I think this should be all for today's training, because for the surface treatment, my training slide has already combined all of the key information in this ES standard together. So simply speaking, surface treatment is complex. It would have lots of different types of failures. So always be cautious. And if our supplier has anything not clear or has any concern about our requirement on the drawing, please tell them, feel free to contact our VNN teams and contact me, of course. And we, Material Group, would support from the technical side.
Yes. So thank you. And so on behalf of the vendors, I'm so very thankful for your useful and informative training today as well.
Yeah, always my pleasure, and always good, always a pleasant journey working with VNN teams. Yep.
Yeah. Thank you, everyone. Yeah.
Thank you,
So
everyone. Yep.
yeah, you will share the training material after this, right?
Yep. Just
So
after the meeting, I would send you that.
yeah, thank you. Yeah. Thank you,
Yeah.
everyone. Yeah. Bye bye.
Yeah. Thank you. Bye bye.
Have a nice day.